We're trying to find a nice question to ask in our theory. So now we're ready to state what that question is. So let's draw a space-time diagram. Okay. Let's draw a space-time diagram. So there is t. There is x. And I want to draw the world line of light. And from the discussion that we've just had, we know it is a 45-degree line. So I'll just label this as world line of light. Okay, now, what is the question that we're going to ask? It is the following. We're going to say, imagine we release our particle from position x is equal to 0 at time t is equal to 0. Okay, so we release our particle from the origin. It evolves, so it will do whatever it likes. It'll move where it likes or whatever, but it evolves its dynamics. It evolves according to the Hamiltonian H. The Hamiltonian H is going to tell us how this particle will move. And then the question that we're going to ask is, what is the probability that we detect the particle at position x, let me call it xp, some particular x position at time tp. Okay, so let's pick a TP. Maybe TP sits over here. And let's say that I consider an XP sitting over here. So I want to know what's the probability that the particle moved from the origin to this point X over here. Now, you might not have good intuition about what that probability amplitude or probability should look like. Actually, me neither, so don't feel bad. I also don't have a good intuition, but we'll calculate it just now. But one thing that I do know, if you ask me what's the probability that the particle will land up at this position, well, in this case, I would say that the probability should be 0. Why should the probability be 0? Well, you see, in this time TP, that's how far light could travel. To get to this point over here, this is how far our particle would have to travel. So our particle would have to travel further than light can travel, but nothing can travel faster than light. So I would expect that probability to be 0. For this other case, well, in this case, the probability might well be non-zero. It's interesting to see what it is. So the reason why this is a good question to ask is that we actually know what we expect of the answer. We expect the probability is going to be 0 for this yellow possibility. We expect the probability will be non-zero for this blue probability. Okay? And it's going to be interesting to calculate it and see exactly what it is. Now, you can see that it's rather interesting, but the points lying on this green line, they've got a special role. These are the points which lie on the line x is equal to t or t is equal to x. The points that are lying like this yellow point, these are points that have x, which is greater than t, and the points like this blue point are points which have x less than t. And later on, we're going to see that these three different types of points have some important meaning. This x less than t, so where we would expect a particle can travel to, those are going to be called time-like separated. So the red and the blue point will be time-like separated, just telling you the names. We'll be coming back to this in a lot more detail. These points, which have x greater than t, we would say the red point and the yellow point are space-like separated. And then these points where x is equal to t, we would say that the red point and the green point are light-like or null separated. But we'll develop those ideas in a lot more detail. And what I'm saying is the probability for our particle to move between two space-like separated points should be 0, because our particle cannot travel faster than light. Well, we're going to calculate this, and it turns out the probability that we calculate over here is going to be non-zero. And that's going to be the problem with our theory. In our theory, using this Hamiltonian to generate the dynamics, it turns out that particles can move faster than light, and that's inconsistent.